few practice problems to get us started. So if we take a look at number, let's do number 20. How can you tell right away that number 20 will be an oxidation reduction reaction? If it ends with an element, we know that the element's oxidation number will be what? 0, right? So that's a quick way, real quick to tell. I was actually looking to see, can anybody find one that's not going to be an oxidation reduction reaction? This is awesome because this means you guys did not do this work last night, probably. What's that? 21, right? We have +1, +1, +1, -2, -2, and then sulfate. We don't even have to look at it because we know if it's sulfate on one side, sulfate on the other side, the oxidation number is going to be the same both ways, right? So let's do 20 real quick. We got +1, +1, 0, -2. So if we're doing this potassium chlorate, then we have -2 times 3 is 6 negative. If you know the charge of any of the chloro polyatomic ions, it's -1. So what plus -6 would equal -1? 5. And this is -1 right here. So we're going from +5 to -1 for chlorine. What's happening to the oxidation number there? Going down. So that means that chlorine has been reduced. And oxygen goes from -2 to 0. So that tells us that oxygen has been oxidized. Kind of an interesting one there. It's called oxidation reduction because oxygen is usually a great oxidizer, which makes sense, or it's great at causing something to lose their electrons. In this case, oxygen has been oxidized itself. So let's take a look. If KClO3, if the Cl was reduced, that makes this the oxidizer. Make sure, circle the oxidizing agent and underline the reducing agent. If we take a look here, since there's only one reactant, not only is this big old thing here the oxidizing agent, it is also the reducing agent. What's the question, Monk? Molecule as a whole. You are totally correct. Yeah. The molecule as a whole. But as we know, like when oxygen started forming around the Earth, if there was any iron or anything like that, the O2 that was produced would start to corrode that iron and those metals, right? The oxygen element can also be like the oxygen compound O2. All right. Just for fun. Actually, no, we're good. We're good on that. Let's no need to do that. All right. Plenty of practice there for you. Let's take a look then at the 2 types of cells. Let's see if we can make one of these. I had to make a test for Thursday, so I didn't have time. And now we're having some ominous meeting on Thursday. Yeah, this is interesting. We're all the teachers are meeting in person. Yeah, right? Who's making this weird choice? Very interesting. Huh? That's what I was wondering. Not fired, but maybe step down, right? Oh. Dun, dun, dun. All right, so let's take a look then. Here we, what's that? You guys are amazing. Somebody tried to get me, that Emma girl. She was like, you have, she actually, what is it? Yeah, what is it? The big one? TikTok. And yeah, Anna. I don't think it was Macy. It was you would have to do this. Oh, Trisler? Yeah, Georgia. What? Uh-huh. Dude, I only saw him for like what, semester and a month or two. Yeah, but TikTok, yeah, I think I had to do the other one. What's the mind running one or the maze running with Macy? Oh yeah, you did like that. But nothing was cooler than the Healy nunchuck. Oh yeah. That was amazing. Oh. All right, back to chemistry. Two types of cells, galvanic and electrolytic. Galvanic has a bunch of different names, voltaic or electrochemical. Volta, he wasn't the first one to make the galvanic cell. Oh, what did he make? He called it the voltaic stack. And basically, you could make one of these at home. It's kind of cool. You take salt water and you basically take pennies and zinc washers and you put like a napkin soaked in salt water between it. And then you basically stack each one of these on top of each other. The more stacking you get, the more powerful that voltaic stack will be. It's kind of interesting. I don't know if you remember last year we watched the movie dealing with Humphrey Davies, but that voltaic stack was what allowed Humphrey Davies to actually discover many elements. For example, sodium and potassium. Before that, nobody actually could use electrolysis to basically pull those metals out of soda ash and potash. That's actually where the names come from. Soda ash, they were able to extract sodium out of that, and potash, they were able to extract potassium out of that. Kind of interesting. It's also called the Daniel cell because I believe the scientist that is accredited with making it, even though we call it voltaic cell as well, is something Daniel. I don't know his first name. Yeah, right. He's like a scientist that made the thing. And we're going to go ahead and give this to Volta, Volta. But yeah, it's kind of interesting. So a cell is a device capable of generating electrical energy for chemical reactions. We're going to hopefully make two cells back there. What we call them half cells. The cell itself is both of these half cells put together. A galvanic or voltaic cell is spontaneous. So yesterday we saw a spontaneous reaction for who? The zinc and the zinc forming the copper, right? And we didn't see a spontaneous reaction for the penny reacting with the zinc sulfate. They generate electrical energy without substantial activation energy. Electrolytic cells are not spontaneous. So as I said, we could take that non-spontaneous one and turn that half cell into electrolytic cell by putting energy into it. Your generation, I mean, what was the age that you got your first cell phone, Monk? 8th grade. Anybody younger than that? 8th grade? 7th grade. Oh, it's competition now. At home players, we're at 7th grade for first cell phone. I came out of the womb with mine. No. But so a cell phone is a perfect example of a voltaic cell and an electrolytic cell. It's a voltaic cell whenever you're powered up and you're running your cell phone and you're doing your apps. It's an electrolytic cell when you're recharging that battery on there, that lithium ion battery. I think it's the most common one. I don't know of any cell phones that don't come with that now, right? So there we go. Let's take a look here. Here is an example. So if we take a look, here we have copper being the anode. The anode is where oxidation takes place. Oxidation is a loss of electrons. The electrons are going to go to the cathode. So remember, when we look at the reduction potentials of these, reduction is gain. This silver is going to have a higher reduction potential than the copper. And we're going to get the electrons to go up onto this wire. And you guys are in physics, right? So you know what the symbol is. That's a resistor of some type. Those electrons are going to flow to this cathode. In this solution right here is silver ions. As those electrons hit this cathode, the ions in this solution are going to gain those electrons and become solid silver. The copper atoms in this anode, as they lose those electrons, what happens to them? They go into solution. But since the charge here would become positive and the charge over here would in a sense become negative, we need a what's called salt bridge. That salt bridge has ions of, in this case, potassium and chlorine. The potassium ions will go down to counterbalance the negative, and the chlorine will come down to counterbalance the positive. That's the Daniel cell, or the Voltaic, or the galvanic cell. With this, basically what we do is we switch everything around, because instead of having a resistor here, we pump electrons into this using a source battery, a power source, or something like that. So a reaction that is spontaneous in this direction is non-spontaneous in this direction. But what can we do to make it spontaneous? We add electricity. By adding that electricity, we then basically reverse that entire cycle. Over time, what's going to happen to the mass of the copper anode in the galvanic cell? It will go down. If we're looking at the metal itself, we're not destroying the copper atoms, but if we're looking at the mass of the piece of metal itself, it will go down because copper ions are forming from that and going into solution. What will happen to the mass of the silver? It will go up because it's pulling atoms, ions out and forming atoms of silver along that piece of metal. And what causes this to not be effective over time? And we're going to use silver and copper, even though we know that we don't have that type of battery in our phones or whatnot. What causes this to lose charge over time? Imperfections. The crystallizing of the metal or whatnot does not crystallize right, or you get impurities to start forming, things like that, preventing the anode from forming correctly whenever you're going in the opposite direction. Yes. What is what? Because if you look down here, this solution is basically that's erosion, right? So it's forming something that's soluble in here. That copper 2 plus ion coming off of here is going to be dissolved into that solution. Usually, like for example, that's copper 2 sulfate back there. So if I put a piece of copper into that, whenever we lose electrons, it's going to basically form that ion. That's what the copper ion is. And that copper is soluble. It's not that metallic, it's not undergoing that metallic bonding anymore. Clear or no, need more? And that's also why if you have that plus, that positive coming into this solution, it needs to be counterbalanced by that negative. All right. Cool. So let's see what this says after that description. See if I missed anything. A galvanic cell is a device where chemical energy is changed into electrical energy. We've covered that. It works on a spontaneous reaction. We've covered that. Constructed of 2 half cells. Covered that. 1 for oxidation. Oxidation is where the anode occurs. And 1 for reduction. Reduction is where the cathode occurs. In a galvanic cell, what can we do for that? Anode starts with A and oxidation starts with O, and they're both vowels, right? If you're trying to figure out a way to remember it. 2 cells with solution in them, 2 electrodes that are metal rods inserted, anode, the metal that undergoes the oxidation. Yes, covered since electrons are produced here, negative charge. Yes, that's a good point. So if you're looking at a terminal of a battery, the anode is the negative and the cathode is the positive. So a cat. Yeah, what is there? There's some weird one. Maybe I've got it down here. It's like fat cat or something. External wire. That's the path that the electrons are allowed to flow. The salt bridge contains some type of salt that will not precipitate in either of the solutions and allows the charge to balance out. The salt's anode travels toward anions travel toward the anode, and the cations travel toward the cathode. So here's a fun thing. That's actually where anion and cation comes from. Originally, it was anode and cathode, but the anions travel to the anode, and the cations travel to the cathode. Fun fact there, if you wondered where those names came from. Each cell has an overall charge that remains 0, balanced by the influx of cations or anions. Notice the values for the voltage. There's a term called electromotive force. This is used a lot more in chemistry than voltage. Do they use that in physics at all? Okay. EMF. And basically, it's the force that pushes the electrons between the 2 points. The voltage is positive if it's spontaneous and negative if it's non-spontaneous. Therefore, reaction with positive voltage will occur in what we call a voltaic cell, and non-negative if you are looking at an electrolytic cell. This is the one we're going to try to build back here. And here's one other way that you can write this notation. An electrode plus the cation plus the other electrode. Now, think about it this way. If we take a look, the first one written starts with A. So that is where the anode of the battery is. This one line tells you that they're in the same cell. This double line tells you that they're separate half cells. Anode is always on the left. Hey, here you go. Here's some little memorization things. Anode, A and O, oxidation, cathode, and then they have the negative and the positive. Think about cat. All right. Let's build this thing. That might be it today. It might take us 15 minutes to build this. Let's try it. Stop share. Oh, you're gonna watch me build one. You guys yesterday, you're like, no more labs, no more labs. Right? What's the point of that? It's a lot of work. Yeah, right? Like I said. How stable is that one? What's that? Boiled Gatorade? Yes. Here's the cooler of the two, right? What was that? What about? They just jumped from somewhere? Don't know. All right. This guy. Well. Mm-hmm. Fun. Salt Bridge. Oh, these are nasty. And so this is what's that? Good one.
Looks like your turn started fine.
Oh yeah.
You're going so fast.
What I want is like a higher grit.
Fortunately,
Like the softest in the world. But yeah, this is what I wanted to be doing yesterday instead of making it a test, but
oh, it's true.
so what's the point of me doing this? Yeah, right. What's on there? Is it zinc or not? Right, right. Hmm? What's it doing? And I want to get part up here too. What this is going to do is this is going to cause my voltaic cell to not be. That's good, right? Unfortunately. Look at that. Right. This guy. Just making sure we get it a little bit cleaner than it is. Two. That might be good enough. You ever touch pennies and you can taste them? It's my superpower. All right. Hmm?
Fingers. Tastes like
Everyone who's touched them before? Hmm. Zinc. So I want to put this in zinc. Starting our first cell there. And our second cell here. Maybe. Right? Zinc sulfate. 1 molar. This is a poison, remember? What's that? And 1 molar copper 2 sulfate. Let me get these a little bit more fair. Obviously, we're doing qualitative with this. How many of you have ever watched Breaking Bad series?
Oh, for sure.
Remember whenever the RV battery died because Jesse put the key in there? Basically, we're doing what Dr. White did. Still is a doctor. Remember, he worked for a pharmaceutical company before. But you guys said you watched it.
I didn't watch all of it.
Oh,
I started right up. I ended it.
let's
I
just
started
end this
watching,
conversation
right when
now.
right when he got hired by that dude that works at the chicken place.
Those photos?
Yeah. Yeah, he saw his new big meth lab.
Yeah.
And then I just kind of
All right.
that was hot.
You used to think that Miss Cotton was going to do that?
Yeah.
That's kind of amazing. Push a button and all of a sudden I'm downstairs like that guy. Remember whenever it got real weird and Siraj kept trying to go back there every chance he got, and then he stole my candy? Oh, wait. Never forget. All right. You guys have used one of these before? That's a milliamp meter. I don't want a milliamp meter on a voltmeter. It's a voltmeter. Wish I had like cool banana clips. This thing is older than me for sure. All right, what's it say? 0. Viewers at home, 0. Why does it say 0? No salt bridge. Said we wanted a classroom pet. We've got one.
So
Some halophile. Like there's some organism growing in there. Oh, dude. Yep. What should we name him?
I killed him.
Kill him.
Oh, we should name him how? We'll just resettle, right?
Yeah.
Is that just a super?
What are
saturated-
you doing?
Is that a super
That's from that?
saturated solution? Huh?
It is. It's not super saturated. It's just saturated. So the bridge here, I'm just going to stick this in here. We can get class pictures with them. Huh? Yay. It's a piece of paper. So I've got the salt bridge here. And we're going to put that in there.
Oh,
And look at that.
an eighth of a volt.
Yeah, right. We've got a small amount of a volt here, about 0.25 volts. For home, I don't know if you can see this or not, but can you see that little needle?
I can't.
This needs to be 4K.
Yeah, right. But yeah, definitely. Let me see if I can, because it's all very hard and difficult to move. Let's see if I can get it a little bit closer. See there?
Yeah, I can kind of see it.
Yeah. So if we take away the salt bridge, notice down, put the salt bridge back on, boom. We just made a battery. Imagine if we were able to go back in time, anywhere even to show volt of this. Be like, that's amazing, right? What's that?
I said, because, yes, because what I would do with the time machine is show hold on to the battery.
Dude, could you imagine how you would change the world? Or go back and make a test?
Battery, like, 2 years before we made a battery.
He made a voltaic stack. Different. I think that's gonna do it for today because I don't want to get into math.
Let's go.
So that's it for today, guys. If you have questions, by all means, stick around. I am going to talk a little bit more. If you want to leave, you're more than welcome to. But I was going to talk about the final a little bit if you wanted to. Is there anybody that even wants to take a final? Because I don't want to not have a. I don't want to get here on the day of the final and be like, I need to do my grade, and then I'm basically going to ask you to sit down with me for 25 minutes and let's talk chemistry, right? What is that called? What do the English teachers always do? Or we'll do an oral exam. But if there was a high need for this, what I was going to do is I was going to make basically, I think, make it worth 33 points, and that would be 1315 FRQ, and then however many multiple choice it takes to get up to 33, and then multiply everything by 3. And I don't, yeah, right. So, I mean, that would be the final. That's something I could make quickly. It doesn't sound fun to me either. Yay. Have a great day.